Hello, everybody. My name is Justin, and I'm going to be talking about using MATLAB to simulate a quantum computer. For our agenda, I'm going to start off by discussing why MATLAB is a really nice tool for modeling the behavior of qubits and their interactions with quantum gates. Then I'm going to give a little bit of a mathematical background on the Deutsch mathematical model of a quantum computer, where quantum states and quantum gates can be represented by using matrices. And once this foundation is established, I'm going to be showing off some of my own MATLAB functions that I wrote in order to demonstrate how MATLAB is so intuitive and relatively effortless when it comes to modeling quantum behavior. And this will hopefully provide some inspiration for you to want to create your own quantum simulator. Finally, I'm going to be discussing existing quantum simulators that use MATLAB, and I'm going to make some suggestions as to how these simulators could potentially be improved. So, what makes MATLAB such a good tool? Well, MATLAB was designed for computational mathematics, and it's a matrix-based language. As a matter of fact, seen in the first bullet point here, we see that MATLAB actually stands for Matrix Laboratory, and it specializes in matrix operations. Also, MATLAB has built-in matrix functions, such as finding the trace or the inverse of matrix, and finding the tensor product between two matrices. In addition to being a tool for matrix operations, MATLAB also recognizes the letter I as an imaginary number, and it can handle operations that involve complex numbers. So some built-in functions for complex numbers include finding the angle of a complex number, or its complex conjugate, or even plotting a complex number. Finally, MATLAB has excellent plotting functions to visualize data. So on the next few slides, we're going to see why this is all such good news for creating a quantum simulator. So we're going to start off by talking about the states held by the qubits and how they could be represented by using matrices. So we can represent qubit states as a one-column matrix, as shown right here, and the number of rows in the matrix is equal to 2 to the n, where n is the number of qubits involved. So in this first example here, we see that the first row corresponds to a state of 0, while the second row corresponds to the state 1. And the numbers in these states may contain imaginary numbers, but the magnitude of these states cannot exceed 1. So when normalized, as seen in this third bullet point here, the states must add to a probability of 1. So on the next slide, we're going to be discussing the quantum gates that could be applied to these states. Quantum gate operations can be represented as unitary matrices, which could be applied to the state matrices by using matrix multiplication. There are a number of different types of gates that could be either real, imaginary, or complex. So on the next slide, the Hadamard gate is going to be used as an example of applying a quantum gate to a 1-qubit state. In this example, a Hadamard gate is being applied to a 1-qubit state where the probability of measuring state 0 is equal to 1, while the probability of measuring state 1 is equal to 0. And this is the initial state of the qubit. After the matrix multiplication is completed and the gate has been applied, we see that the new qubit state is either in state 0 with probability 1/2 or in state 1 with probability 1/2. So this is an operation that could easily be done by using MATLAB. So on the next slide, I'm going to show you my 1-qubit Hadamard gate function that I created. The 1-qubit Hadamard gate function takes a quantum state such as 1, 0, or 1 over square root of 2, 1 over square root of 2 as input and outputs the probability of each state after it goes through the Hadamard gate. The function also plots the probability of each state by using a bar graph, as shown below. So the function begins by declaring a 2 by 2 unitary Hadamard matrix and creating a column vector to represent the current state, or the initial state. Then we see that line 4 performs the matrix multiplication that was seen on the previous example in the previous slide. And afterwards, the probability for each state is calculated and plotted on the bar graph. So the picture on the right shows the same output as calculated in the previous slide. So on the next slide, I'm going to be showing a 1-qubit y-gate function as well. Now, the y-gate function is nearly identical to the Hadamard gate function, with the exception that a different unitary matrix is being applied to the state. So this function was written to show that MATLAB also could perform computations using imaginary numbers or complex numbers. So the fact that MATLAB has such a great toolkit for matrix operations, imaginary numbers, and data plotting makes it a very good tool for a beginner to create their own quantum simulator. And in addition to being able to create your own quantum simulator, there are also existing quantum computer simulator toolkits that you could download for MATLAB, which we will see on the next slide. One existing quantum computer simulator toolkit that I found is called Quantum Computer Simulator, written by Martin Vesely. This simulator uses matrices to model quantum states and uses matrix multiplication and tensor product to represent quantum gate operations. The result of running the simulation is a measurement probability distribution, which comes from normalizing the state vectors. This simulation is characterized by its main function called quantum computer, which is responsible for running quantum algorithms. The first input to the quantum computer function is called Q algorithm, and this is the quantum circuit that's going to be simulated. So this works with any number of qubits, and it uses all of the well-known quantum gates. As shown in the examples below, we see that putting a space between each gate will cause the gates to be placed on the same qubit row, while putting a semicolon between them will cause the gates to be placed on separate qubit rows. The next input to the algorithm is measured qubits. And this input, you put the qubits that you wish to put through the quantum circuit. And finally, the last input is the initial state vector. And this must be entered as a one-column matrix with 2 to the n rows, where n is the number of measured qubits. Unfortunately, the simulator is not able to check if these initial states are able to be normalized, so the user should watch out for that before inputting it as the initial state. So shown below are some examples for inputs for the initial state. So as you can see here, 1 over square root of 2, 1 over square root of 2 normalizes to 1, and so does 1 half, 1 half, 1 half, 1 half. And now it's time to run the function. So here's an example of a 3-qubit circuit being run by using the quantum computer function. It has an initial state of 1 in the first state and 0 in all of the other 7 states, as shown right here. And the function returns 4 outputs. And these outputs include a graph of the probability distribution for each state, a vector of each output state, the probability distribution of the output states, and the overall matrix operation that was applied to the initial qubit state. This output is known as alg, and it's not included in this slide. But in our case, alg is equal to the Hadamard matrices multiplied by the swap gates matrices. The quantum computer function has its limits, so it's suggested that you only run small quantum circuits on it. I tried working with a different number of qubits, and I ended up finding that 14 qubits was the cutoff point at which the algorithm would start to take around 10 minutes to run. And this is probably because of the print statements as well as updating the graph. But overall, if you keep the algorithm as it is, it will take around 10 minutes to run at 14 qubits. So if we compare this to IBM's Circuit Composer on their browser, the output states that are calculated when you create the circuit are computed almost instantaneously. However, the measurement probabilities, if you were to click this drop-down tab and click on measurement probabilities, IBM's not able to display these probabilities when it comes to circuits that are over 9 qubits. So I would recommend using IBM's simulator if all you need is the state vector, but if you would like to calculate the measurement probabilities, you may have to actually wait 10 minutes and use the quantum computer function. Now that we're finished talking about the quantum computer function, I want to give an honorable mention to another quantum computer simulator called Quack, which was created by Professor Rode at the University of Queensland in Australia. This simulator contains functions that would be a great addition to our current simulator of interest, such as the circuit printing function and a measure function. Unfortunately, Quack was discontinued in 2014, and the software is nowhere to be found on the internet. However, Quack still influenced me to make these suggestions for the simulator that we are currently looking at, and I could uh, correspond here. The z measure function would be a great measurement function to add to the current simulator, as well as this print the quantum circuit function. Uh, One way you could maybe do the z measure function is to use a random number generator and correspond it to the probabilities that we're working with to create a random measurement. And finally, the last suggestion was to check for a normalized state vector to ensure that the user is not putting in an illegal state for the qubits. Finally, here's an example of sample code running from the Quack quantum simulator. Although the program no longer exists, there's still some code out there that could inspire you to recreate the simulator or improve an existing one. Thank you for listening to this presentation. Here are my references, and are there any questions?